Alright, after being clickbaited by the last video's thumbnail, I'm finally going to do something actual, factual, and useful. This episode, one episode is divided into parts. For episode 1, we have 3 parts, so that is 3 videos worth of content. For episode 2, that is bondings and electronegativity. That's one. That's episode. I'm planning like 5 parts, 7 parts and stuff, because that is quite a big topic, but enough ado for now. Let's start the first part. Oh, my microphone just dropped. This part is purely storytelling. This part we are talking about the history of atoms. Also, I think this is my first drawing ever shown on YouTube. And of course, those drawings are very ugly and inaccurate, right? Alright, our story of atoms begins in a philosophy phase. In ancient Greek, some philosophers thought that matter is made up with indestructible particles, and they called it atomos. This means indivisible and indestructible. And this is the origin of the modern English word, atom. At this point, no actual solid evidence was found. All is brainstorming. And it will keep that way for thousands of years. How pathetic. This is a chemistry class, not a philosophy class, so I will fast forward thousands of years. I'm a bad storyteller, yay! The time just blasts to early 800s, 800s. The major event that happens is John Dalton's law of multiple proportions. Proportions? Why did I say proportional? I suck! So those chemical formulas are not useful for now, but we'll see the contents. So tin, a metal. Tin is a metal. That metal has 2 kinds of oxides. One is a white powder and one is a black powder. Actually, I'm not supposed to say it's a powder because that could be any form. One is white and one is black. That is 2 kinds of oxides of tin. And the first one, for every 100 grams of tin, it contains 13.5 grams of oxygen. And for the second one, it contains 27 grams of oxygen. 13.5 over 27 is a nice proportion of 1 over 2. That is a very simple integer proportion. And those chemical formulas were unknown at the time, and they only know that the compounds contain tin and oxygen in it, and they calculated how much oxygen it contained for every such amount of tin. And they found that they are in simple proportions. Not only does the oxide of tin do it, the oxide of nitrogen obeys this law as well, and many other compounds like the chlorides of iron, I don't know. So let's just list 3 oxides of nitrogen. Nitrous oxide, also known as laughing gas, nitric oxide, and nitrogen dioxide. For every 140 grams of nitrogen, the first one contains 80 grams of oxygen, the second one contains 160, and the last one contains 320. These 3 numbers make a very simple proportion of 1 over 2 over 4. Am I supposed to call that over? I don't know. If we add in nitrous anhydride and nitric anhydride here, we'll get a very nice continuous proportion of 1 over 2 over 3 over 4 over 5. At the time, I think nitrous anhydride was too unstable to be discovered, so I think it is just 1 over 2 over 4 over 5. But those reveal very simple, nice-looking integer proportions. Please be aware of that those chemical formulas were in existence at the time of the discoveries. These formulas were inexistent, and without the formulas, they discovered these proportions. This seem to reveal something fundamental about the nature of matter. The time fast forward to the year 1827. The major event is that a botanist, Robert Brown, discovered Brownian motion. A second very inaccurate and ugly painting shows up. When pollen particles are suspended in water, they move randomly for whatever reasons, and the whatever reasons will be revealed later. It was suggested that particles, I think these are made up of atoms, but let's just call them particles. Matter is made up of very small particles. Those particles of water were bumping into the pollen particles randomly to make them move. Alright, we fast forward 60 years. The time, is that 60 years? Or is that, I suck. This is an 8. This is an 8. We fast forward to 1887. The major event is Thomson's discovery of the electrons. Electrons is a fundamental part of chemistry. In fact, all chemical changes is just revolving around electrons. It's just atoms throwing electrons to each other, against each other, playing electrons with each other. That's it. Electrons will be our arch nemesis, will be our worst enemies or best friends in our course of chemistry. Anyways, Thomson discovers that cathode rays are not electromagnetic waves. What are electromagnetic waves? I think you have learned that in physics class. Cathode rays is that in a very high voltage, let's just say this power source is a very high voltage, then electrons will go from this way. Electrons will go from this way. And they will shoot from the cathode and bump into air particles or whatever it is. Those high energy electrons will make light. This thing is called a cathode ray tube. A cathode ray tube. It is supposed to make light when it is attached to a very high voltage power source because of a particle. Those particles are not electromagnetic waves, which is something explained in physics. I forgot what it is. But they are rather extremely light particles. It was not hard to prove that these particles are those particles that transmit electricity. So it was very intuitive and uncreative naming conventions. They are called electrons. Electrons. What we will be dealing with in a long time, for a long time. He proposed a plum pudding model. He suggested electrons are evenly distributed across the whole atom. An atom is a sphere. Atom is a sphere of positive charge, and then on the outside of the sphere, and I think inside of the sphere, there are electrons like embedded in them, electrons everywhere. It definitely don't work this way. It's just a model proposed in ancient times. He suggested that electrons are evenly distributed across the whole atoms, which is a sea of evenly distributed positive charge. The diagram looks like a plum pudding, which I don't think it is true, but they think it is true, according to hungry scientists. Hence the name, the plum pudding model. You gotta remember that. It's gonna be very important. You gotta remember that. Time goes to 1908. There is a this is very, very important. A super significant experiment in the history of chemistry, the Geiger-Marsden experiment. Alpha rays, which are positively charged rays. From a modern perspective, alpha rays are helium nuclei, but we don't talk about that. We call that alpha rays. They are positively charged rays. They have positive charge. They were sent to bombard a thin sheet of gold foil, and observations on the interactions were made. The gold foils will interact the pathways of the alpha rays. Most of the alpha rays passed right through the gold foil. Those alpha rays just pass through the gold foil as if the foil was non-existent, but some of them got their paths altered. They interact with the gold foil, and then the foil somehow makes their paths rotate by a small angle. A very small amount of them get deflected, which means they go attack the gold foil, then the foil just reflect them and change their path so that they go in the opposite direction and hit this side of the wall instead of this side. How to make the observations? Well, the wall is made of a special material so that it fluoresces when hit by an alpha particle. But anyways, we can make observations about the trajectories of those alpha particles. Then, a very important observation. Very few of them got bounced right back in the exact same direction. Very few of them. What does this suggest? Alpha rays are of positive charge, so to bounce them back, you need a concentrated portion of positive charge. Then, if the alpha rays hit right at the positive charge concentrated region, it will get deflected or just reflected back. If it goes nearby the region, it will have this trajectory altered. And if it goes nowhere near the region, it will pass right through, right? That is a very reasonable guess. Well, hypothesis, we don't say guess. If the plum pudding model was correct, then the alpha rays should behave almost identically, so the plum pudding model was invalid. Small numbers of alpha particles getting deflected clearly indicated that there is a small, dense, positive charge-rich region at the center of an atom, with electrons surrounding it. Electrons surround the dense region. This region is called the nucleus. The plural form of nucleus is nuclei, if chemistry isn't weird enough, okay? There comes a very more reasonable model. Rutherford's atomic model. Rutherford proposed that electrons orbit a small nucleus, much like planets orbit the sun. This is a simple explanation, but it has been outphased, yet many schools still use it because it is very simple and useful. This model better fits the experiment. According to the plum pudding model, the alpha rays will just pass through, or getting deflected. I don't care, but yeah, they should behave in a very different ways than experiments predicted. Well, yeah. For the Rutherford model, then it worked very well. A large number of them getting passed right through. So all of these empty regions like the alpha rays, if they go through the empty region, of course they are going to pass through. When they go near the nucleus, the charge of the nucleus is going to propel them so that alter their path. If they go really near the nucleus, the repulsive force will be pretty strong so that the trajectory can deflect it. If it right hits at the nucleus, it will bounce off. This is a pretty elegant solution and explanation. And this is the basis of practically all modern atomic models, I guess. Time goes to 1913. The major event that the Bohr's atomic model got proposed. Robert Bohr proposed a model that electrons orbit the nucleus in such a way that there are only finite orbits. Keywords: finite orbits. how do the planets orbit the sun? They can orbit the sun at many distances. That could be like 1 unit, like 2 units, 100 units. There could be many possible orbits for a planet. But for electrons, there are only finitely many of them. Electrons spontaneously jump between orbits via observation of photons. The orbits are discrete, which is the opposite of continuous, because according to the quantum theory, I think I misspelled again, energy is discrete, which means quantized in integer portions, have a unit. Yeah, I can't explain it better. However, this model suggested that electrons orbit the nucleus in a predictable pattern, in a accurately predictable orbit, which is not true according to the quantum theory. Here goes the Schrodinger's atomic model, which is, I think it is still used today. Yeah, I think it is still used today. According to the Heisenberg's uncertainty principle, which is a fancy science word, saying that microscopic particles can't have their position and momentum determined at the same time. This fancy equation, the Planck constant, rendering the idea of fixed electron orbits obsolete. Instead, Schrödinger proposed a model where electrons are described as three-dimensional wave functions. This is too complicated for a chemistry class, so none of that for now. The Bose model will be widely used in the following courses for ionization energy and stuff, and for that heavy physics knowledge will be used anyways. So you just know that the Schrodinger model is the one used today. I'm not gonna talk about it because I don't understand it. If I do understand it, I won't be talking about it at YouTube. I would have a much brighter fate. Anyways, the equations show that there are regions around the nucleus where the electrons are most likely to be located in. Keywords likely, because nothing is predictable in the microscopic world. These regions are called electron orbitals. This model is the dominant and accepted model of an atom today. Time is 1932. The event is the discovery of the neutron. Sometimes when an atom of an element can have different mass, we say that the element has isotopes. The nuclei of isotopes have the same charge, but different mass. It is proposed that particles called protons are responsible for the positive charge of the nucleus, and they are held together by neutrons, which are neutral, so they are called neutrons, and they weigh almost as much as protons. The mass difference of isotopes can be explained by the difference of numbers of neutrons. Because you have the same amount of protons responsible for the charge, then you have different amount of neutrons to hold them together. And that could be vary in number. Here we got a complete timeline. In whatever BC, there's a philosophy phase. In the early 1800s, the law of multiple proportions got proposed. 1827, the Brownian motion. 1887, the discovery of the electron. There goes the Townsend's model. There goes the Rutherford's model in 1908. The Bose model, which we are gonna use very frequently, in 1913. The Schrodinger's model in 1928. Then finally the discovery of the neutron in 1932. At least for now, the dust of what's in an atom has settled down. These are very inaccurate depictions of a nitrogen 14 atom according to different models. There goes the plum pudding model, doesn't look like a pudding at all. There goes the Rutherford model, different orbits, variable orbits. There goes the Bose model, discrete orbits. There goes the Schrodinger's model, those orbitals, regions where electrons could be in that I drew pretty poorly. Then there's a pretty colorful post-neutron discovery depiction where I drew the neutrons out and the protons. I think that's it for this video. Thanks for watching. I'll see you next video. I have all the presentations ready. I don't have the time to record this now. I'm gonna upload this and I'm gonna go to sleep. Thank you for watching.